Hello, good evening all. Welcome to the interactive section of NPTEL course Fundamentals of Spectroscopy by Sain Bachi and Anirban Hastra. And I am Suvarna Sujilkumar, TA for this course. Let's start this week interactive section. Is my slide visible now? Hello, hello. Is my screen shared to you? So let's start. Last week we had discussion about rotational spectroscopy, rotational spectroscopy and the correlation between the linear motion and angular discussed. Followed by the mathematical expression for the angular momentum we have discussed. Followed by we discussed about rigid rotor approximation and the criteria for a molecule to be microwave active. The mathematical expression for the reduced mass and moment of inertia of the system has been established, followed by the mathematical expression for the rotational constant B. And we described about the rotational energy level and the selection rule in that rotational spectroscopy. We discussed about the rotational spectrum, how it will look, how we will interpret the data. Then, what is the use of rotational spectroscopy? One can find the internuclear distance between atom using rotational spectroscopy, followed by how we will interpret the isotopic effect in rotational spectroscopy have been discussed, followed by the degeneracy in the rotational spectroscopy discussed. This week we had to watch 5 videos. In the first video, it starts with the discussion about the degeneracy in the rotational spectroscopy. We already know that if the rotational quantum number J, if J is the rotational quantum number, the degeneracy is given by Gj is equal to 2J plus 1, right? This we already know. If J is equal to 2, we have Mj quantum number with the values -2, -1, 0, 1, and 2. So, it is five-fold degenerate. Okay. So the delta Mj, the selection rule is given by 0 plus or minus 1. This all we have discussed earlier. So with an energy, with the same energy in a rotational spectroscopy, five energy levels are, five degenerate states are possible. Their orientation is given by the value Mj, right? Followed by, we discussed about the Stark effect. Consider an electric field is applied to a molecule in a particular direction. There will be interaction between the electric field and the dipole moment of the molecule, right? So this interaction depends upon the spatial orientation of the molecule. So the energy of the system now depend upon the value of Mj as well as delta Mj, right? So this will affect the rotational spectrum. Thus, the degeneracy will be lifted, and the lifting of degeneracy in the presence of an externally applied electric field is known as Stark effect. Right. Okay. So without the presence of an electric field, the energy levels will be degenerate. In the presence of an electric field, the degeneracy will be lifted. Right. So if you have a quantum number J is equal to 7, in principle, we have 2J plus 1 orientations. In the presence of an electric field, it will have J plus 1 orientation. So the energy levels will be split at such a way that let this will be 0 and we have plus or minus 1 followed by plus or minus 2 and plus or minus 3 plus or minus 4. This is plus or minus 5 and plus or minus 6 plus or minus 7. Correct. So the degeneracy lifting has happened in the presence of an external electric field. The energy for the system is given by, it depends upon J as well as Mj, is given by Bj into J plus 1 Hc plus Aj. There is a constant, A constant which depends upon both A as well as Mj, and the momentum, and a term which responsible for the which have component of the electric field. Okay, this A term mathematically can be represented as Aj Mj equal to J into J plus 1 minus 3 Mj square divided by 2B into J plus 1, 2J minus 1, 2J plus 3. Okay, this is the mathematical expression for the AJMJ, the constant that we found if the molecule is in the presence of electric field, the energy can be given by that equation. Correct. This all discussed in the lecture videos. So we are just recapping that. Followed by the intensity of rotational levels have been discussed. The population of any state is given by the Maxwell-Boltzmann distribution, which can be represented as for a state, the number of population, the state n with respect to a population of the state m is given by this mathematical expression. Right. This term represents the degeneracy of n state, and this Gm represents the degeneracy of m state. Correct. Where Gn is greater than Gm. Okay. Consider a system where J is equal to 0 and J is equal to J. So we have to find the Maxwell-Boltzmann distribution for the state. So let's do that. So for a state nj to n0, since the j is equal to 0, we can write gj divided by g0. Since the j is equal to 0, the degeneracy of the state will be 1. So we directly write 1 e raised to minus delta E divided by RT. Correct. We already know the uh, expression for delta E, and that for a degeneracy with a quantum number J also we already know that is given by 2J plus 1 into E raised to minus BHCJ into J plus 1 divided by KT. Right. So if you could find the derivative of this, that is dnj d by dj of nj by n0 here is equal to 0, then j is equal to j max. So our find the j max where the intensity, the population, where it is maximum, right? So if you do this differentiation, you will get a mathematical expression for the j max, which is given by j max is equal to root of RT divided by 2BHC minus 1 by 2. Okay. So one graph also discussed over here. Let's just go through that. So this can be Nj divided by N0. So this, the increasing values of J, where the degeneracy will have a linear relationship to J plus 1. With increasing value of J, we will have a distribution of with the maximum where d by dj of nj by n0 equal to 0. This point we will get j max, right? And this graph represents the variation of difference in the energy. That is e raised to minus delta E divided by kT can be represented as the exponential decrease in the graph. So we are just recapping what all are the topic covered in last week. So consider a experimentally obtained rotational energy levels of which can be roughly represented as it's a bit difficult to draw like this actually. Okay. So this distance we already know that is 2b, and this transition is given by 0 to 1, and this is 1 to 0 according to our selection rule. This will be 1 to 2, and this will be 2 to 3, and this will be 3 to 4, and this will be 4 to 5, right? So followed by we derived the expression of J max from our Nj by N0 value. I hope you can do that. That is in the video itself. We have done in the video, sir has discussed about that. So in the next lecture, the detailed description of non-rigid rotor have been done, where non-rigid rotor essentially means that the bond distance between two atoms is changing. In rigid rotor approximation, what we did, we assume that there is no any difference in the bond length between the atoms. Here in non-rigid rotor, there can be difference in the bond length of the atom. Okay. So in the rotational, experimentally obtained rotational spectra of a carbon monoxide molecule, when the increasing the J value, of course, the difference delta energy between in each levels has been increased, but a difference in the energy between the successive states, there will be considerable decrease has been observed at higher J values. Okay, when the J value is very higher, the energy gap between two subsequent energy level is getting that energy difference is getting lower. So what will be the reason for that? For that, we are explaining the rigid rotor model, where it can be the rigid rotor we can represent it as two ob- uh, mass of object which are connected by a spring which can move, right? So when it rotates, there will be a force which makes them outwards. This is known as a centrifugal force, or this effect is known as a centrifugal effect, right? If the value of J increases, what happen? The B value will decrease, right? Moreover, when the molecules are under the influence of centrifugal distortion, the distance between the molecules are getting higher, right? The distance between R will be greater than if they are not rotating. So the in moment of inertia, we already know that is directly proportional to R square. So moment of inertia and the rotational constant is inversely proportional, right? So as a result, there will be, so when the I increases, B will be decreased. The B and the energy between two subsecutive uh, energy levels is directly proportional. So when the B decreases, the energy gap between two adjacent J levels will decrease. So the in the presence of an if you are considering the non-rigid rotor, the energy with this centrifugal distortion is given by in terms of wave number by this expression, where D represent the centrifugal constant. Okay, how we can represent this in a, more clear manner? See, two objective of mass m1 and m2 are rotating about an axis. This is the center of mass of the system with an angular velocity omega. Okay, this picture we can actually represent as a one body problem where a mass of mu, which is reduced mass object, is rotating about an axis, right? Let the r0 is the distance where there is no rotation. Upon the rotation with an angular velocity omega, the distance between the distance between the axis of rotation and the object has increased. Let it be that distance r. Sorry, guys. So let's derive this formula. The centrifugal force is given by Fc is equal to mu v square by r. This can be also represented as mu omega square r. Right. The restoring force against the centrifugal force is given by K into R minus R0, where this K is the force constant, not the Boltzmann constant. This is a force constant for this system. So at equilibrium, Fc is equal to Fr, right? So we can equate this equation, two equations, 2 omega square R is equal to K into R minus R0, right? From this, we can arrive a equation for R, where it's given by K R0 divided by K minus mu omega square, right? So The expression for a energy expression for a non-rigid rotor in terms of wave number is given by Bj into j plus 1 minus d into j plus 1 the whole square. Right. Okay. So what is the energy of this any system? That is the sum of kinetic energy plus potential energy. What is in our system we can write it's half I omega square plus half k r minus r0 the whole square. Okay, this we already familiar in the case of rigid rotor approximation, right? So let's substitute this r term here, half I omega square plus half k mu square omega raised to 4 r square divided by r square, sorry, k square. So this we can write half I omega square plus 1 by 2 I omega square the whole square divided by half k square. Right. This can be also half L square by 2I. We already know there is expression where L can be written as root of j into j plus 1 into h cut. Right. Using this, we can arrive a expression where Ej can be written as h square divided by 8 pi square I j into j plus 1 plus h raised to 4 divided by 32 pi raised to 4 j square k square j into j plus 1 whole square. Right. We can represent this expression in terms of the wave number as well, which is given by that is Ej divided by Hc, right? Bj into j plus 1 plus h cube divided by 32 pi raised to 4 I square k r square c j into j plus 1 the whole square. Right? Following the derivation, we have represent this equation in a more simpler format because it's a very big equation, no? So we represented as nu bar j is equal to Bj into j plus 1 minus 4b cube by nu bar square j into j plus 1 the whole square. Where b this term is given by b is given by h by 8 pi square IC, right? We can write that which is d is equal to 4b cube by nu bar square. Now the expression will be bj into j plus 1 minus d into j into j plus 1 the whole square. Right. From here, we can get an expression for B effective, which is given by B minus dj into j plus 1 into j into j plus 1. Right. So this can be represented as a B effective. So the equation will be for B effective will be B effective is equal to B minus dj into j plus 1. So under rotation, when we consider non-rigid rotor, the B value will be somewhat lesser than the rotational constant B that we used in the rigid rotor approximation. Right. By this, the energy difference between two rotational states that we have evaluated, how we will do that? We can find the energy level, right, by using the expression for the energy in terms of the wave number. So the delta nu j bar is given by nu bar plus j plus 1 state minus nu bar at jth state. Right. We just derived the expression for how to find the delta nu j bar. Giving the states, you will get the expression for delta nu j bar in difference in the energy levels in terms of wave number is given by 2b into j plus 1 minus 4d j plus 1 the whole cube. Okay. So that was that second lecture. The third lecture was about polyatomic molecule. First, the video described about angular momentum. It can be represented as L is equal to I omega. Here, angular momentum as well as the angular velocity are vector. Here, this I is the tensor, which is the moment of inertia. The tensor is represented as a 3 by 3 matrix. So it has 9 components. So we can write this expression in a matrix form as well, where Lx, Ly, Lz will be the resultant matrix, and we will have a diagonal term of I like this and off diagonal term as well. Yeah. So please write the off diagonal terms. Okay. So the and followed by the angular velocity terms. Oh, let's write off diagonal term. X, Y, I, X, Z, I, Y, X, I, Z, X, I, Z, Y, I, Y, Z. Right. So in this off diagonal elements of moment of inertia, we can write it as in terms of the principal axis of inertia, which in terms of A, B, and C. Okay, let's do that. IA, IB, and IC with others term are 0. Other matrix elements are 0. This is IC. Okay. So with respect to principal axis of inertia, we have 3 principal moment of inertia, IA, IB, and IC. Among this, IA is the minimum value and IC will have the maximum value, right? So considering this, we have classified the molecule into different top or rotors. Let's look into the linear rotor, where consider the molecule consider the 3 axes as this, and the molecule is along its A axis, A principal axis, and this is the B, and this is C. Okay. So the moment of inertia with respect to the A axis, that is IA is equal to 0 here, followed by IB equal to IC. Right. So this will be exhibited by the molecule like HCl, OCS, and carbon monoxide, carbon dioxide. But the carbon dioxide won't be rotationally active, that we already know, since it doesn't possess the permanent magnetic moment, right? Followed by, we classified this polyatomic molecule in spherical top, symmetric top, and asymmetric top. Let's have a quick recap of all of them. So it will be easy to do questions then. So for a spherical rotor, we have IA is equal to IB is equal to IC, right? Examples are CH4, SF6, and C60. CH4 is a tetrahedral geometry, SF6 has an octahedral geometry, and C60 has an isosahedral geometry. Okay. Another category of molecule is a symmetric rotors. Symmetric rotors further divided into prolate. It's given by IA less than IB is equal to IC. Examples are CH3Cl, CH3CN, SF5Cl. Okay. Another category of symmetric rotor is oblate. It given by IA equal to IB, which is less than IC. Example are CH3Cl, CHCl3, sorry, and BF3, BCl3, and benzene. Okay, these are like disc-like molecules will be oblate usually, right? Followed by for a polyatomic molecule, for example, OCS, we derive the expression for the magnetic moment, which given by I is equal to M0 R. Okay, we can derive, just express that pictorial representation of the molecule. Then it will be easy to understand. See the molecule oxygen, MO is sitting over here, followed by molecule of carbon, that is mass is given by MC, followed by the sulfur, mass is given by MS. Okay, so this will be its center of mass. The distance to center of mass is given by from carbon R. See, from oxygen it's given by RO. To sulfur, to center of mass distance is given by RS. Okay. So the mathematical expression for the moment of inertia of the system is given by M0 R's distance of R's CO, that we can represent it as RO minus RC, plus MS mass of sulfur, RSC square minus M0 C0, MCRCS the whole square divided by M. Okay. Followed by the last fourth lecture, we have discussed about water molecule and its moment, principal axis of moments and its moment of inertia. So consider on the water molecule, we can write a picture. Where an oxygen sitting over here along the Z axis. The distance to center of mass from the hydrogen is given as F. Oh, guys, this will take time. Maybe we will not get much time to do question. So I'm just skipping this. So this is already in the video also. Please check it out that. So in the last lecture, we have recap the selection rule via quantum mechanics perspective. For an intensity of a transition is directly proportional to transition moment integral, which is given by integral psi r star. This is a dipole moment operator to psi r d2. So this is the final state. This is the initial state of the wave function, right? So followed by the we tried to obtain the eigenfunction of a rotating diatomic molecule, considering a diatomic molecule A and B, which is rotating about an axis with an angular velocity omega. This can be also represented as a one body problem where an object is rotating with an angular velocity of omega with a reduced mass of mu, right? Good. This we have already done. By the expression of classical kinetic energy, we can write K is equal to L square divided by 2I, where L is the angular momentum, I is the moment of inertia. We know that, right? Where I can be represented as a mu r square, that is a moment reduced mass of the molecule. So the Hamiltonian for this system is given by angular moment operator L square divided by 2I, where L is the angular momentum operator and I is the moment of inertia. Corresponding Schrodinger equation is given by L square is the operator 2I psi r is equal to E psi r. Here psi r is the function of the system and E is the eigenvalue, right? So this eigenfunction is actually represented in the form of spherical harmonics. The mathematical expression for this we can write as follows, which is a function of theta and a phi. Right. So this theta, this is known as a associated Legendre function, which consists of a normalization constant. And this function can be in the form of an exponential term as you see here, right? Followed by we will derive the selection rules in the framework of quantum mechanics. The selection rule is given by delta L is equal to plus or minus 1 and delta M, which is equal to 0 and plus or minus 1, and delta J, which is given by plus or minus 1. So these are the selection rule that we have discussed. Professor has discussed in the lecture video. We had to watch that. Okay. With this introduction, let's move to the question answer section. I hope everyone can see the question and try to answer it. Okay. So the first question, lifting of degeneracy in the presence of externally applied magnetic field is known as. Any thoughts? Any answer? It's Stark effect. We already discussed that. The answer is Stark effect. In the presence of an electric field, there will be shifting of or lifting of degeneracy in the rotational energy level happen. This is the Stark effect. In the absence of electric field, the degeneracy is given by 2j plus 1. In the presence of an electric field, the degeneracy will be j plus 1. Right. That we have given examples in the, we explained in the beginning itself of the class. Right. So if you have a quantum number j, it can have, without the presence of an electric field, it can have a degeneracy with 2j plus 1. Say the j is equal to 2. Values possible are given by orientation is given by mj to 2, 1, 0, minus 1, minus 2. This is 5, 4 degenerate. In the presence of electric field, it will be shifted to j plus 1 with the value 0, 1, 2 with the, for a quantum number j is equal to 2. Right. Which of the molecule are not spherical rotors? SF6, SiO2, CCl4, CHBr3.
SF6 first answer, ma'am.
Yeah. Uh, Actually, got it. Which are not spherical rotors. So SF6 is a spherical rotor, right? CCl4 is also spherical rotor. What is the criteria for a spherical rotor? That is IA is equal to IB is equal to IC, right? So this condition will be
Okay.
followed by these two. So which are not, that is given by these two. Correct.
Okay, ma'am.
The next question, the degeneracy can be given by which expression? This we have discussed a lot of time. For a quantum number j, what will be the degeneracy for the rotational system? This is the normal case, okay, without the presence of a magnetic field and all. But it will be any thoughts, any answers?
Sorry, ma'am. One.
Huh? Hello?
Hello.
Yes. Okay. The answer is 2j
Okay.
plus 1. Okay. The answer is 2j plus 1. That we already discussed in the last class as well. this class also, for a rotational quantum number j, the degeneracy
Okay,
is given by 2j plus 1. If j is equal to 2, we have a five-fold degeneracy with 2, 1, 0, -1, and -2. So that is the answer. Next question, the Maxwell-Boltzmann distribution between two states, where I is the ground state and j is the excited state, can be written as, we have four options.
third answer, ma'am.
Third, sure.
Yes, ma'am.
Mm, can you please check again? Sure. We have to check what is the sign of delta E, how the number of population as well as the degeneracy term are connected, right? So the answer is this one, the second one.
Okay.
Okay. So we have to just see the question carefully. Maybe we know the answer, but it may be just confusing. So what we have to
Yes,
think,
ma'am.
the degeneracy and the population are directly proportional, right? If we have
Okay.
Ni by Nj, the degeneracy will be Ji only, right? It won't be Gj, Gi, Gj, and the relation between e raised to minus delta I. So the answer is
Okay,
B,
ma'am.
right?
Okay.
So the next question, what is the spacing between two pure rotational spectral line? B, 2b, 4b, 8b. I think we have discussed this last week also, where we can simulate the rotational spectra. Eh, Anybody remember? No?
Second, ma'am.
Or
2B.
yes, the answer is 2b.
Second answer, 2B.
Yeah, yeah. And next question, what is the correct moment of inertia relation for prolate rotor? So what is the correct moment of inertia relation for prolate rotor?
One minute, I'm confused.
Uh, Please.
One second, please.
Second,
What is the correct moment of
prolate rotor.
direction of
Okay. For the symmetric rotors are divided into two, prolate and oblate, right?
Yes, ma'am.
Yeah. So for a prolate rotor, we have the condition IA less than IB, which is equal to IC. Right. These are rod like, and examples are CH3Cl,
Ma'am, please screen.
CH3, uh, answer C, right?
मैम स्क्रीन डिस्प्ले नहीं हो रहा.
Yeah, can you repeat, please?
स्क्रीन प्रॉब्लम आ रहा है मैम. क्वेश्चन ही डिस्प्ले नहीं हुआ विंडो पे.
Okay, okay. So I'm not presenting. My question is not visible.
नो मैम.
Okay. Oh, this happened just now, right? Last question you could see, right?
यस.
Is now question visible to all? Hello.
यस मैम.
Okay, thank you.
हेलो.
So for yes, thank you. Now visible, right?
यस मैम.
Okay, thank you. So for a prolate, the correct moment of inertia relationship is given by I A. The moment of inertia about A principal axis will be less than IB equal to IC. So this is the
ओके.
relationship for the example CH3CF, CH3CF, and SF5CF. Right. So another category of symmetric rotor is oblate. The condition for oblate is IA equal to IB, which is less than IC. Okay. Examples are CH, CL3, BF3, and BCL3, and benzene. Okay. So the answer
ओके.
is C. The next question, water can be classified as a spherical top, symmetric top, or asymmetric top, none of the above. Any thoughts? Water can be classified as
फोर्थ मैम.
none of the above.
नो
Is that?
नॉट sources energy and else the
Uh, so let me explain. It's a asymmetric torque, right?
can
What is the condition for asymmetric torque? IA not equal to IB not equal to IC. So when all the principal moments are not equal, it will be an asymmetric rotor. So water is one of that kind. One of the example, water and H2O2 will be fall in this. Okay. So the next question, from the following molecule, there is one prolate and one oblate. Choose the correct combination. One is prolate and another is oblate. Any thoughts?
Third answer, ma'am. CH3CHN.
Yes, correct. Correct. Where CH3CN is a prolate, where what is the condition for a prolate? We just discussed IA less than IB, which is equal to IC. And carbon dioxide is a linear rotor, right?
Yes, ma'am.
Yeah. For a linear rotor, we have IA is equal to 0, followed by IB is equal to IC. Correct.
Nice.
And C6
Yes, ma'am.
H6 benzene is a oblate, which is a subcategory of symmetric rotor, where IA equal to IB, which is less than IC. And finally,
Yes, ma'am.
SF6 is a spherical rotor, right?
Yes.
Spherical rotor with the condition all the principal moments are equal. Okay. The next
Okay, ma'am.
question. Which of the following relation is not associated with the rotational selection rule? It's not associated. Okay.
Yes, ma'am.
Which of the following relation is not associated with the rotational selection rule? The molecule must have a permanent dipole moment. Another delta L is equal to plus or minus 1. Delta M is equal to 0 plus or minus 1. The molecule must have a temporary dipole moment. That is the primary criteria for a rotational, a molecule to be active in a rotational spectra.
Confused, ma'am. For second and third.
These are what, correct or not? The answer is not associated.
One. Okay.
So, for a molecule to be rotationally active, or the should it have a permanent or a temporary dipole moment?
First.
Yeah, it should have a permanent dipole moment, right? So the
Okay, ma'am.
selection rule for L is given by plus or minus 1. That is also correct. Selection rule
Yes.
delta ML, that is given by 0 and plus or minus 1. This is also right. It is not associated with the rotational selection rule is this one. So the answer is the molecule must have a temporary dipole moment. Correct?
Yes,
Okay.
ma'am.
Thank you.
How?
The next one, rotational eigenfunction are known as spherical harmonics, Hamiltonian, Jacobian, transition moment integrals. Rotational eigenfunctions are known as spherical harmonics, Hamiltonian, Jacobian, transition moment integrals. Any thoughts?
First one, ma'am.
Yeah, yes, correct. Spherical harmonic. Okay. For a
Okay, ma'am.
rotational eigenfunction, we can represent it as with an operator L square 2I with the wave function psi r, eigen value E with a psi r. So the operator, momentum operator, energy operator acting on the wave function psi r gives back the wave function with a constant E. Here E is the eigen value, psi r is the eigen function, right? So the psi r is represented as spherical harmonics. It's depend upon the theta and phi.
Yes.
The psi r can be represented as in this as a spherical harmonics, a function of theta and phi, which can be represented as function of phi. Okay, here this
Okay.
function usually will be in the form of before that this part is known as a associated Legendre function. It consists of a normalization constant as well. Okay,
Okay, ma'am.
the normalization constant is given by 1 by root 2 pi. Okay, the answer is spherical harmonics. The rotational
First.
eigenfunctions are represented as a spherical harmonic. So next question, among the following molecule, which one shows pure rotation spectra? Which one shows pure rotation spectra?
First one, ma'am.
What is the criteria a molecule to be rotational active in a rotational spectra? It should have a permanent dipole moment, right? The structure of N2 is how?
Yes.
Right. So the dipole moment will cancel each other, right? So it won't have any
Yes,
dipole
ma'am.
moment. What about carbon dioxide? It's also the same, right? For
Yes.
CCl4, since it has a tetrahedral structure, the individual dipole moment will cancel, resulting it has a zero dipole moment. So the answer is H2S, right? A molecule having no permanent dipole moment does not generate the oscillating electric field on rotation and hence cannot interact with the radiation. Such a molecule does not exhibit a rotational spectrum. The essential criteria for a molecule to be exhibit rotational spectrum is that it must have a permanent dipole moment. Right. The molecule with permanent dipole moments are known as microwave active molecule. So here H2S is the answer. It has a bend shape, so it resultant dipole moment won't cancel. So H2S is the answer. Clear?
Okay, ma'am.
Thank you. So the next question, quantized rotational energy of the molecule is given as. What is the expression for the rotational energy level of a molecule? That's the meaning of this question. A simple rotational motion of a molecule in a rigid rotor approximation. No need to worry about the non-rigid rotor in the framework of rigid rotor approximation. What is the answer?
No, ma'am, no
Okay,
idea.
okay. Okay, okay. The answer is this. So this actually we have wrote many times where j into j plus 1 h square divided by 8 pi square I. Okay, this is the equation for a quantized rotational
Okay.
energy of the molecule. Right, this familiar with this terms. But what is j here? J is the rotational quantum number. I is the moment of inertia. I can be represented as mu r square, where mu is the
Okay.
reduced mass and r is the distance to the center of mass. Okay.
Okay.
And next question. Centrifugal forces due to rotation of a molecule about any given axis tend to options increase the moment of inertia about the axis, decrease the effective rotational constant, both A and B, none of these. So the centrifugal force due to rotation of the molecule about any axis, what it will do with the moment of inertia or rotational constant. Here they asked about the moment of inertia and here about the rotational constant B. So we just discussed about the centrifugal force. So when the molecule is rotating, consider the molecule M in the non-rigid approximation. We consider they are bound, they are closed by a spring-like. Uh, there is a spring-like motion we can just see. So the bond length altering is possible. So when the molecule rotates the omega velocity, there will be a force to outward. That is a centrifugal force F C. The mathematical expression for the F C is given by mu B square divided by R, which can be represented as mu omega square R also. Yeah. So this we have discussed. So what happened when this centrifugal force acting? What happened to the moment of inertia and what happened to the D band?
Okay, ma'am.
We can just think like the molecule is rotating. So essentially what will happen? We said that since the molecule are rotating, the bond length will increase, right?
Okay, ma'am.
So what happened to I? Since R is increasing, expression for mu R square is I is mu R square. When R increase, I will increase, right? Moment of inertia
Yes.
will increase.
Yes.
So the what is the relationship between the moment of inertia and I? Moment of inertia and B. The B rotational constant and the moment of inertia is inversely proportional. We must have written somewhere. Yeah. Okay. Then let's discuss with this answer. So when the I increases, so we reached till I will be increased, right? When the R increases. So the moment of inertia and I is inversely proportional. So in effect, rotational constant will decrease. So the answer is
Okay.
when the molecule rotating perpendicular to the principal axis experience an outward force that we discussed, centrifugal force. Then this force is called centrifugal force. Due to centrifugal force, the bond length of the molecule can increase. So the moment of inertia decreases. That we discussed, right?
Yes, ma'am.
Moment of inertia increases. So the rotational constant decreases. Since the moment of inertia and the rotational constant are inversely proportional. Inversely proportional. Okay. So the answer is the centrifugal due to moment of inertia increases and the rotational
Yes.
constant decreases. The answer is C. Okay. Yeah.
Yes, ma'am.
So this is a numerical question. Okay. The H2 molecule has a reduced mass given here in kilogram and an equilibrium nuclear distance that's R also given here. The rotational energy we have to find in terms of the rotational quantum number J. The options also given here. So where we will start? We have to find what? Rotational energy, right? So the what is the equation for a
Yes.
rotational energy? That is E is equal to h cut square divided by 2I into j into j plus 1. Right.
Yes, ma'am.
Okay. For this, we have to know the I value. That is the moment of inertia. How we can find? We can find, right? They have I mathematically given by mr square. Where mass is given, r also given. We can find that. And this expression we can write when you remove the cut value. Cut h cut means h divided by 2 pi. So we write the equation as h square divided by 8 pi square mu r square into j plus 1. Now we are not worrying about this term, okay? Anyway, we have to express the equation in terms of j into j plus 1. Everyone we have seen that, right? So we are not worrying about this term. We only have to solve this entity. Then we will reach to the equation answer. So let's solve that equation. Okay. So is so the equation for EJ is given by h square divided by 8 pi square mu r square into j plus 1. So we are not worrying about j since our all options are in j plus 1, j minus 1 terms. Let it be there. Let's put other constants and find the answer. The value of h is given by 6.6 into 10 raised to minus 34 into 6 the whole square 8 into 3.14 the whole square. Reduced mass is also given in terms of the kilogram 8.35 into 10 raised to minus 28 kg and the mu r square. Okay, so the distance equilibrium nuclear distance is given which is 0.742 into 10 raised to minus 10 meter. This is in all square. So one should make sure that all the variables are in the SI unit, unless your answer will be wrong. So if you solve this, you will reach in a value 7.5 into 10 raised to minus 3 electron volt. This we can write as 7.5 milli electron volt, right? MeV. So this is the simple equation. Only we have to find the moment of inertia where mass is given, the internuclear distance is given. Put in the rotational energy equation as you see here, so that your energy you will get in electron volt terms. Okay, so the EJ will be in this 7.5 milli electron volt with the we missed something, right? we didn't care about j into j plus 1 since our answer has that term as well, j into j plus 1. Since our among the option C is the closest one, we will go with that. So the answer is C. Clear? Only we have to find the only two equation we have to know. The equation for moment of inertia as well as the equation for the rotational energy. Right.
Yes,
Any
ma'am.
doubt?
No, ma'am.
Okay. Thank you. The next question. The transition J is equal to 3 to J is equal to 4 in HCl molecule is associated with radiation of 83.03 centimeter inverse. Use a rigid rotor approximation to calculate moment of inertia and internuclear distance, which means the bond length of HCl. So the transition is J is equal to 3 to J is equal to 4. Right. The transition in the HCl molecule associate the radiation of, this is a hint. Okay. So when you read something like this is connected to an equation or a concept. Right. Okay. Actually, we know an equation where delta nu bar within J is equal to 2B into J plus 1. This is the energy difference between two, if J is equal to J plus 1 to this transition, the energy difference between these two states is given by 2B into J plus 1. Okay, but J is the starting where the transition starts happen. Here the J is given by 3. Right? So for this transition is an energy associated with this given by 83.03 centimeter inverse. So when we put in this equation delta nu J bar J is equal to 3, we will get 2B into 3 plus 1 and it will be 8B. Okay, this is our prior knowledge. If you know this equation, we should come into conclusion that so, okay, the radiation energy associated with the transition is given. It should be correlated with the energy gap between these two states. So we wrote the equation like this, and we find the delta E in terms of centimeter inverse associated with this transition. So this should be equal to 83.03 centimeter inverse. This is the um, clue, or this is the what a starting point in the system in the question. Till now, it's clear. Is it clear? Clear? Okay,
Yes,
I
ma'am.
hope it. Okay. From this, we can easily find B, right? 83.03 centimeter inverse divided by 8. If you do the math, it will be 10.83 centimeter inverse. So we got the B value.
Yes, ma'am.
Okay. So what we have to find?
Yes,
Moment
ma'am.
of inertia and internuclear distance. Right. So we have
Yes, ma'am.
an equation which connects moment of inertia and the B, which is B is equal to H divided by 8 pi square IC.
Yes.
Now can we find I, the moment of inertia? We can, right? Right. We
Yes,
already
ma'am.
found the value of B. Others are constant. Then I is equal to H divided by 8 pi square BC. Okay, our value is in centimeter inverse. Okay, so if you put all the variables, you will get the moment of inertia as 2.7 into 10 raised to minus 10 gram centimeter inverse. Okay, no, centimeter square. Okay. Okay, now we have to find what? Internuclear distance. How we will find internuclear distance? There is an equation connecting I is equal to mu r square. Right. We have to find the r. We already know the I. Do we know the mu or the mass of the system? Of course, yes, right? HCl molecule is given. Molecule chemical formula is given. With that we can find the reduced mass. Right. Reduced mass of HCl is given by mass of H into mass of Cl divided by mass of H plus mass of Cl. So this will be we just substitute and find the value. It will be 1.61 into 10 raised to minus 24 gram. Okay, so now we know the moment of inertia. We already know the reduced mass from the HCl formula. Now we can easily find the R value. So R is given by root of I by mu, where I we already calculated, which is 2.7 into 10 raised to minus 40 gram centimeter square, and 1.6 into 10 raised to minus 24 gram is the mass when the internuclear distance between hydrogen and chlorine in the HCl molecule will be 1.29 into 10 raised to minus 8 centimeter, or this can be represented as 1.29 angstrom. Okay, since we represented centimeter, when we convert to angstrom, it is 1.29 angstrom. Okay, clear?
Yes, ma'am.
Okay, thank you. The next question, Hi and Di are made to undergo the same transition from J is equal to 0 to J is equal to 1. The light frequency causing the transition for Hi equals 1. So the frequency for transition for Hi is V, that value we taken as V. Approximately which frequency would you expect to induce the same transition in Di? So this is a concept-based question. So we have to see what is the relationship between molecular mass and energy associated with the transition. So when we see this kind of questions, these thoughts should be coming to our mind. Is there any relation? Because only difference Hi and Di is the molecular mass. They have different in terms of their molecular mass. They have other difference also, but preliminary they have difference in their molecular mass. Is there any relationship between the change in molecular mass and the frequency for a transition or energy for a transition? For a energy for a transition, we just now wrote an expression, right? For a transition, whenever you heard the name, it will be associated with the delta E, nothing but. So try to think in that direction. You have given the transition range from j is equal to 0 to j is equal to 1, that you have to take care. So when the transition you heard and the j value is also given, try to correlate with that equation. The equation is given by delta E is equal to 2b into j plus 1, right? Right. So here j is equal to 0. Since the transition happened from j is equal to 0 to j is equal to 1. When we put in the equation, delta E is equal to 2b into 0 plus 1, which is equal to 2b. Clear?
Yes, ma'am.
Okay. So, what is the expression for a B? B is given by h square divided by 8 pi square what? I, right? Is this I term has a mass term, molecular mass term? Right. So the moment of inertia can be represented as mu r square. So the rotational constant is inversely proportional to the mu, right? Clear? The rotational constant is directly proportional to delta E. Okay. So what is the relationship between the delta E and mu? We will write like this then. It will be simplified. So the delta E is inversely proportional to mu. Correct. So when, so we can write in a mathematical formula for our convenience. So we will get their exact relationship. So the delta E of di to the delta E of hi is related to mu hi to mu di, since they are in inverse relationship. Okay. So what is this ratio is given? It's 1 by 2. Since the molecular mass of deuterium is uh, deuterium have twice the mass of hydrogen. So the approximate frequency that we can expect for a same transition for di will be so this value is actually given as V here. It's V by 2. The transition that is for a HI, the transition energy is given by or the frequency is given by V. And for a transition for a DI, it will be half of the HI. Clear? So only basically you have to know the relationship between the delta E and the rotational constant and delta E and the reduced mass. Clear?
Yes, ma'am.
Thank you. Next question. In a hydrogen molecule, okay, hydrogen molecule, when hydrogen is replaced by deuterium, what will happen to the rotational constant? Is it increase? Is it decrease? It becomes 0, remains same. So this is all our relation based question. We have to know the equation, how they are related, and think appropriately. Uh, any idea? We just here actually we see a relation, no? Relationship between the rotational constant and moment of inertia. Can we put that here and think? Here also basically what we are actually changing, it's a molecular mass. And the hydrogen is replaced by deuterium. Essentially, the molecular mass is the one changing. What will happen to the rotational constant B? So the relation connecting rotational constant B is equal to h square divided by 8 pi square I, where I is the moment of inertia. So we can write h square I pi 8 pi square mu r square. Right? When hydrogen molecule is replaced by deuterium molecule, what is happening? Let it be the molecular mass m. Let it is molecular mass m dash. M dash will be greater than m. Right? So, what is the relationship between the rotational constant and molecular mass? It's inversely proportional. So, the b divided by b dash equal to m dash divided by m. It is in the inverse relationship. Since the m dash is greater than m, the b dash will be less than b. Right? So, what happened? It will decrease. Correct. Any doubt?
No, ma'am.
Thank you. So the next question, the third lowest microwave absorption frequency. Okay, third lowest microwave absorption frequency of a C13 or 16 is given in megahertz. The second lowest absorption frequency of a normal isotope of carbon is in the C12 should be at. So the third lowest microwave absorption frequency of C13 carbon is given. We have to find the second lowest absorption frequency of C12, that is a normal isotope. How we will think? Okay, let me put together. So here mentioned third lowest microwave absorption. So in the absorption or microwave spectra, the third lowest absorption frequency means it's at 6B position. So actually the third lowest microwave absorption corresponding to a 6B value in the spectra, which is here as 33657 megahertz in value. Okay. The second lowest absorption frequency, it actually implies 4p. Okay. This is the one we have to find. Correct. We already know that. From here, we can find the value of B, right? We already know that the B is inversely proportional to the molecular mass. Okay, let's put together equation. The rotational constant for C13, let's write the normal isotope carbon first, O16 carbon monoxide to the C13 labeled. So this will have an inverse relationship, right? With the reduced mass. The mass of C30 to O60, the reduced mass of C12 to O16. Right. Clear? So let's put together in these equations where three threes. We have this equation and we already know the parameter as well as the reduced mass of the system. We have to find the reduced mass. I already mentioned the formula where M1, M2 divided by M1 plus M2. For any diatomic molecule with mass M1 and M2, we can find the reduced mass as follows. So you find the reduced mass and substitute in the equation. It will be if you do the math, you will get an value which it is 57,627. Okay. This value is corresponding to what? The rotational constant for the C12O16 is this value. Okay. So now we had to find for 4B of C12O16. How we will do that? We just multiply with the 4, right? 4 into 57.6, 57,727.58. The final answer will be which is in the option uh, the option is bit confusing. Maybe the answer is this one. Okay. Okay. The second law was absorption frequency. Second law was absorption frequency. Um, there is a problem with the option, I guess. I hope you know how to solve the how to approach the problem. I think there is a problem with the options, I guess. The answer is not in the option. It's okay. Sorry for that. I didn't check the um, options. So essentially, what we have to find, we have to know the relationship connecting the reduced reduced mass and the rotational constant. If you know these two parameters, we can play around it and find the answer of that. Maybe we will redo this question next time. The option has some problem. Rest is fine. Okay, we will wind up our discussion session now. Are there any question? If not, thank you all. Let's meet next week.
Okay, ma'am. Thank you.
Welcome.